Hello guys, this is third unit. This is of magnetic materials. So we are going to cover about magnetic materials. So you know the applications of magnetic materials. It is used in electrical meters, dynamos, motors, transformers, computers. For memory or storage, we are using only magnetic materials only. Televisions and nuclear magnetic resonance equipment and particle accelerators. So we'll be using magnetic materials, especially for the memory storage purpose. We'll be going for the magnetic materials. How magnetic materials are used as a magnetic memory storage device? It's a very big question. Okay. That is because of the spin of the magnetic material. Okay. Now we'll see some basic terms of magnetic materials. Then we will go how the magnetism is created in the magnet, and then we will see something about hysteresis law and ferromagnetic materials. Okay, so now we are going to see about some basic terms. So magnetic dipole moment means the two equal and opposite poles which is separated by a distance, just like electric dipole. Okay, so electric dipole, you have two and opposite charges separated by a distance, but here in magnetic dipole moment, which is represented by two and equal opposite poles or separated by the distance g. So that is known as magnetic dipole moment. Magnetic flux, it is defined as the total number of magnetic flux lines passing through the surface. Okay, that is known as magnetic flux. So I'll show what is meant by magnetic flux. Can you able to see? This is the north pole of the magnet and this is the south pole of magnet. So now just see the magnetic field line which passes through the surface. So this is known as magnetic flux. If the magnetic flux is high, then we can say that magnetic field is high. If the magnetic flux is low, then we can say the magnetic field is low. Okay. So what is magnetic flux? It is So the magnetic flux is the total number of magnetic field lines passing through the surface. That is known as magnetic flux. Now next one is magnetic induction. It is the same thing, but it is when a total number of magnetic flux line passing through a unit cross section. Okay, that is magnetic induction B is equal to phi by A. Magnetic flux is phi and magnetic induction is phi by A. Okay, so what is magnetic induction? It is total number of magnetic flux line just passing through a unit area. Okay, and the unit for magnetic flux intensity or magnetic induction is Weber per meter squared. Unit for magnetic flux is Weber. Okay. Now the magnetic field intensity, it is the force experienced by the pole strength of the magnetic material. Okay, the force experienced by the magnetic field, that is H is equal to F by M. We know the unit for force is Newton and magnetic pole is Weber, so Newton per Weber. So this is magnetic field intensity. These are the very important two terms. Magnetic induction, just total number of lines passing through a unit area. Magnetic field intensity, it is a force experienced by the magnetic field, magnetic pole. Now the intensity of magnetism, it is the ratio of dipole magnet per unit volume. Okay, I is equal to M by V. So here what is M? M is the magnetic dipole moment per unit volume. Okay, so that is magnetization. Okay, intensity of magnetization. The next term is magnetic susceptibility. It is the ratio of intensity to the magnetic field intensity. The intensity of magnetization to the magnetic field intensity. Psi is equal to I by H. Okay, it is the amount Magnetic susceptibility is the ratio of intensity of magnetization to magnetic field, and I'll explain what is magnetic intensity, magnetic magnetic intensity is. Magnetic susceptibility is, it is a ratio of magnetization to the magnetic field intensity. Okay, and next one is magnetic permeability. It is the ratio of magnetic induction to the magnetic field intensity. Okay, so both represents how much amount of magnetic materials get magnetized. This magnetic permeability is represents how much amount of magnetic field lines a magnet is permit, or a material is permitting inside the surface. The relative permittivity is the ratio of mu by mu naught, where mu is absolute permeability, and mu naught is permeability in free space. So this is the relation between susceptibility and permeability. Mu r is equal to 1 plus psi. Okay, just see the equation so that you will understand the derivation. Permeability is equal to 1 plus psi susceptibility. Now you just see this. This is the origin of a magnetic moment. The magnetic moment comes from the orbital and spin motion of electrons. Okay, see here, electron is revolving around the nucleus, and also it will rotate, will have a rotation, that is spin motion. Okay, so the magnetic moment of a material originates from the orbital motion and also the spin motion of the electrons. Okay, so that is the basic of magnetic moment. Okay, so when an electron rotates, when a charge rotates, it will produce a magnetic field. This is a very basic term. Okay, when a charge rotates, it will produce magnetic field, and it will the orbital motion also will produce the magnetic field. Now just see, the electron have orbital motion, the electron have spin motion, spin up and spin down also. Okay, so because of this motion only, because orbital motion and spin motion, will have the magnetic moment. Okay, so this one is the magnetic dipole. As we have seen, the two charges separated by a small distance is known as magnetic dipole. There are types of magnets we have. There is the types of magnets are diamagnetic material, paramagnetic material, ferromagnetic material, ferrimagnetic material. We'll see one by one what are the types. Now you just see, in diamagnetic material, this is a graph between a magnetic field intensity and magnetization. Okay, magnetic induction. So H is magnetic field intensity, M is magnetic induction. Okay, now see, diamagnetic material, atoms have no magnetic moment. Okay, see here, atoms possess no magnetic moment. Okay, that means there is no internal magnetic field inside the diamagnetic material. So whenever, if you apply a magnetic field to the diamagnetic material, there is no change in the behavior. Okay, it won't accept the magnetic field lines inside it. Okay, so diamagnetic material don't have magnetic moment inside. Now we'll just see the paramagnetic material. All spins are aligned randomly. Okay, so if you give, spins are arranged randomly. So if you give magnetic field, it will align towards the magnetic field. Okay, so paramagnetic material have dipole moment or spin inside. Dipole moment and spin both are equal only. Okay, equal, we can say both are equal term. And if they have a spin, all the spins are arranged randomly in the paramagnetic material. Okay, so there is some magnetic field inside the paramagnetic material. Ferromagnetic material, just see, all the spins are arranged properly in ferromagnetic material. So like iron, nickel and all, they are proper ferromagnetic material in which all the spins arranged properly. Now just see antiferromagnetic material, spins are arranged on an anti-parallel manner. Okay, so magnetic moments are arranged, or spins are arranged in an anti-parallel manner. Now with just a ferrimagnetic material, it's have a mixed parallel and anti-parallel lines. So here you see it's a anti-parallel. Here you can see both are parallel. So it is a mixed magnetic moments. So just see, diamagnetic material, there is no magnetic moment. Paramagnetic material, magnetic moment will be there, but it's randomly arranged. Ferromagnetic materials, properly the magnetic moments are arranged. Antiferromagnetic material, anti-parallel, the magnetic moments are arranged anti-parallelly. Ferrimagnetic materials, there is a mixed parallel and anti-parallel magnetic moments. Just see, this is the normal material. Normal material will allow the magnetic field inside. This is magnetic field inside and magnetic field outside. Just see, diamagnetic material, it rejects the magnetic field. It's not allowing the magnetic field. Okay, that is diamagnetic material. Now see, paramagnetic material, it allows some amount of magnetic lines, not all. It will allow some amount of magnetic lines. But if you see ferromagnetic material, it allows most of the magnetic field lines. Okay, so this is the distance between normal and diamagnetic, paramagnetic and ferromagnetic material. So diamagnetic material won't allow the magnetic field lines. But if you see paramagnetic material, it will allow the some amount of magnetic field lines. But if you see ferromagnetic material, it will allow all the magnetic field inside the magnetic field lines inside the material. So the example for diamagnetic materials are gold, germanium, silicon. Example for paramagnetic material, ferric oxide, ferrous sulfate. Example for ferro, iron, cobalt and nickel. So now we'll see the domain theory of ferromagnetic material. Ferromagnetic material is a good type of material. That means it will allow the magnetic field lines inside it. Okay. Example, nickel ion. Okay. So now before going into this, we should know about the domain. What is domain? Domain are the small region which is present inside the paramagnetic material in which the magnetic moments are oriented in a particular direction. Now just see these are domains. Okay. This is one domain, second domain, third domain, fourth domain, fifth, sixth, 7, 8, 9. So we have various domains. Okay, and this is the domain wall, or we can call this one as a Bloch wall. Okay, this is a ferromagnetic material in which all the domains are arranged. There is a lot of domains inside it. In the domains, inside the domain, see the magnetic field lines or magnetic moments are arranged properly. Okay, inside the domains, all the magnetic moments are arranged properly. Here also, see, it's arranged properly. Here also, it's arranged properly. Okay, now this is the ferromagnetic material. Now if you apply magnetic field, all the magnetic moments are aligned parallel to the magnetic field. So this will conduct magnetism. This will become magnetism. So what will happen? All the magnetic moments align properly towards the parallel towards the magnetic external magnetic field. Okay, so this is the ferromagnetic material. So if you consider a ferromagnetic material consists of lot of domains. Inside the domains you have magnetic moments in which magnetic moments are arranged properly. If you apply magnetic field, all the magnetic moments are arranged parallel to the magnetic field and it will become magnetized. Okay, so it will have a suddenly it will become magnetized. Okay, there is a rapid magnetism. So what is domain theory? Domain theory is proposed by Weiss in 1907. It explains the properties of the ferromagnetic materials, hysteresis and properties of the ferromagnetic material. Magnetic domains, ferromagnetic materials divided into small domains. See here, and each domain spontaneously magnetized. So if you apply magnetic field, all the domain will align parallel to the magnetic field. So that means it will get spontaneously magnetized. The direction of the magnetization varies from domain to domain, and the net magnetization is 0 in the absence of external magnetic field. In the absence of external magnetic field, there is no magnetization. There is no the material won't become magnetized. But if you apply magnetic material, there is a spontaneous, this is very, very important, spontaneous magnetization. All the domain magnetic moments will align parallel to the external magnetic material. There are two domains separated by domain wall or Bloch wall. Okay, so the wall is known as the wall. The edge of the domain is known as domain wall or Bloch wall. Okay, when the magnetic field is applied, ferromagnetic material, the magnetization takes place in two ways. So if you apply magnetic field, there are two. The magnetization is due to the two two ways. One is motion of the domain wall. Domain wall itself will move. Another one is rotation of the domain.